Okay, so I believe that the notion of a function is one of the most important ideas in mathematics. In fact, I would go as far to say that almost every idea in pure mathematics can be described in terms of functions. And so in this video, I want to describe what a function is and to show you 7 different ways to visualize functions using arrows, wiring diagrams, fibres, bouquets, graphs, ontology logs, and category theory. So what exactly is a function? Well, basically, it's just where we send every member of some source set to some member of some target set. And so you see here with this red function, I'm sending each of these fruits here, each of these 3 members of this set of fruit, to some member of this target set here, this set of colours. And that's all a function has to do. It just has to send each element of the source set to some element of the target set in some way. Now, obviously, this function has a very kind of natural interpretation in terms of real-world language, but there are other functions too, okay? So, for example, there's a function which just sends each of these fruits to green. It might not have such a natural real-world interpretation, but it still satisfies the definition of a function, in the sense that it sends every member of the source set to some member of the target set. And that's all a function has to do. Okay, so we know what functions are, but what are we going to do with them? Well, we're going to compose them together, okay? So let's now suppose we have another function, a function that goes from this set of colours here to this set of numbers. So here's another function, and you can see that it's sending each of these words here to the number of letters it has. And so now we have this red function, which goes from fruit to colour, and this blue function, which goes from colours to numbers. Well, that means we can compose these functions together. And all that means is that we're going to form a new function by going along the red arrows and then the blue arrows. So we're going to be sending strawberry to 3 because the red function sends strawberry to red, and then the blue function sends red to 3. Similarly, tomato goes to red and then it goes to 3, while banana goes to yellow and then it ends up going to 6. And so we've composed the red and the blue function. And this idea that we can compose functions is what makes them so powerful. Because it basically gives us this way of chaining together these concepts, these aspects, these ways of relating collections of things. So, for example, if I say a man has a left foot and a left foot has a big toe, in a sense, what I'm doing there is I'm composing this kind of function that sends every man to their left foot with the function that sends every left foot to its big toe. And in doing so, I'm associating every man with a big toe. And so here we have it, our first way to visualize functions, which is using arrows. And you've probably seen this before. Now, hopefully I can show you some other ways to visualize functions which will probably be new to you. Okay, so the next way of visualizing functions that I want to take a look at is using wiring diagrams. And these are really fantastic for visualizing situations where we have lots of functions interacting with each other. For example, in a computer program, or if we're forming some kind of a plan of how to do something, like say, cook apple crumble, and we can describe what we want to do in a functional kind of way. And so the idea of wiring diagrams is that we use our wires to represent our sets, and the functions themselves are now just represented by boxes. And so we have this has color function here, and this just takes in a fruit and outputs a color. And once we've got our colour, we can do this blue function here, which is then going to output a number. And so I'm a really big fan of wiring diagrams, and I'm going to try and show you some of the reasons I think they're so useful. One great thing about them is that it's really easy to visualize composition. So suppose we want to do this red function and then this blue function. Well, if we compose those together, we can get a new purple function. And the way that we can visualize this is simply by drawing a bigger box around our wiring diagram. And we can now think of this purple box as this composition. It's a function that takes in a fruit and outputs a number. And the nice thing about this is that we can sort of imagine being able to open the box and actually see how this function works, how it takes in a fruit, determines the colour of the fruit, and then determines the number of letters in the word for that colour. Okay, so here we've got another example of a wiring diagram. This is something a bit more numeric, okay? What this diagram is saying is that we're going to take two numbers, we're going to add them together, that'll give us another number, and then we're going to times it by 3, and that will be our output. Now, one thing that's really notable here is this plus function, because this takes a pair of numbers as inputs and it gives another number as an output. And the notable thing here is that we're representing this by a box that has these two inputs coming in on the left. And so we can represent functions with multiple inputs by having multiple wires going into them. Okay, so it's no secret that I'm a big fan of these wiring diagrams. This is a wiring diagram I used recently for making apple crumble on one of my YouTube videos. And each of these boxes here represents a procedure that we have to carry out, going from the top to the bottom. So for example, this peel and slice function takes in an apple and a knife, and it outputs a prepared apple and a knife. And when we start with these initial ingredients and we follow the steps, we end up with our apple crumble together with some extra sort of components. So I think one of the richest applications of wiring diagrams, and one of the best ways to get really proficient at thinking about functions, is functional programming. So there's a programming language called LabVIEW where one can basically program just about anything just by plugging together different wiring diagrams. So for example, this thing I'm showing here, we could say that this is a function which takes in a couple of numbers, adds them together, and then multiplies the result by 2. So there's this fantastic programming language called LabVIEW, which literally lets you write computer programs by drawing wiring diagrams. So here you see this wiring diagram that takes in a number and then it adds 1 to it and then it times it by 3. And that's a program I wrote in LabVIEW, and you can see that it's going to send the input 1 to the output 6. And it's marvelous that LabVIEW allows you to make all kinds of programs by just constructing these wiring diagrams. Now, some people might say that it's a bit childish to have this sort of visual way of doing programming, but my opinion is that things like this, which allow us to engage our visual cortex, actually make the kind of complicated task of writing programs much easier. Because I believe that most people can understand systems better when they can see a picture of everything that's going on spread in front of them. In fact, my opinion is that one of the reasons a lot of people have difficulty learning computer programming is that the kind of visualizations of what they're actually doing are kind of hidden from them. It's sort of like trying to appreciate classical music just by looking at music sheets instead of actually hearing the music being played. And in fact, my opinion is that these kind of wiring diagrams are actually closer to the kind of pure mathematical core of what's going on underneath these kind of functional programming languages. I mean, the theory of wiring diagrams and how they connect with ideas like monoidal categories is very well developed. And when one appreciates that, one sees wiring diagrams as very kind of clear and expressive structures. And so I highly recommend checking out LabVIEW to anybody who's interested in functional programming. And I also think that this kind of angle has really great potential within education. And if you want to see more about the really interesting things you can do with LabVIEW, you might want to check out my video on cooking monoidal categories and programming. And so here's another thing I think is really neat about wiring diagrams. You see here, we have our first box as a number 3. Now, the inputs of the box are on the left and the outputs are on the right. So if you look at this, you then interpret it as saying, well, 3 is a function, but it has no inputs and it outputs a number. And if you think about it, that actually makes a lot of sense, right? So we can actually think of 3, which you'd normally say, well, 3 is just an element in the set of numbers. But from this perspective, we can actually think of 3 itself as a function. It's just a so-called nullary function. It's a function with no inputs, but it does output a number. It outputs the number 3. And so we're taking that number and then we're going to times it by 2. And that's what this is representing. And so here's some really cool notation. We can write this and say this is just equal to, what's 3 times 2? The number 6. Okay, so this whole thing where we're getting the number 3 and we're timesing it by 2. So grouping these 3 and times 2 boxes together makes this bigger purple box, which simply produces a 6. Okay? So you can see that even the way we evaluate our functions can be represented graphically. Okay, so our third way to visualize functions is to use this notion of fibres. So to begin with, I'll draw our function just using arrows in the same way as we did at the beginning. So we're just literally drawing how these elements are getting mapped by our function. And we'll give this function a name. We'll call it number of cars owned. Okay, so we're trying to represent some data here. Rose doesn't own a car, so the number of cars she owns is 0. Jim, Bob and Rob, each of them own 1 car, and Karen and Julie are fortunate enough to own 2 cars. So we have this function, but notice the way I've set out these different people. I've drawn the people who own 1 car above 1, and I've drawn the people who own 2 cars above 2, and so on. And so this suggests another way of representing how this function is working. And that is to think of there being a sort of stalk or fibre coming up from 0, which holds all of the elements that get mapped to 0. And there's another stalk coming up from 1, which holds Jim, Bob and Rob because they get mapped to 1. And there's another stalk above 2, which holds Karen and Julie because they're the people who get mapped to 2. And so if we have a look at an element in our target set, let's say 1 here, then we can speak of the fibre or the stalk over 1. And that just means the set of elements which get mapped to 1 under this function. Another name for this would be the inverse image of 1 under our function. In other words, the set of elements that get mapped to 1 under our function. And I think that this kind of geometric idea of thinking about stalks / fibres is really helpful. And also because it sort of turns around our view of the function a little bit. I mean, really it seems as though it's the source set now of people who, now it seems as though it's the source set of people now that this kind of perspective makes us focus on more. because we can see how this set of people is partitioned up into these different subsets. The subset of people who own 0 cars, the subset of people who own 1 car, and the subset of people who own 2 cars. Now in this case, this function is not what you call a surjection, okay, because this is a function from people to these numbers, but nothing is getting sent to this number -1. And so if we just deleted that number -1, obviously no one owns -1 cars, well, now we really do just have a partition of this set of people into this collection of 3 non-empty sets. So this kind of view of a function in terms of fibres is very powerful, especially for thinking about things like geometry and dependence type theory. Okay, so now we arrive at our 4th perspective on a function. And I like this one because it's not very well known. It's what we call a bouquet. So the idea is that we have, for our function, we have a source set and a target set. So let's think about this red function here. And so we let the elements of the target set be represented by dots. And then the elements of the source set get represented by petals or loops. And these petals go through the dots which the corresponding elements get mapped to. And so there are 3 petals, strawberry, tomato and grape, corresponding to the elements of the source set. And because strawberry and tomato get mapped to red, these petals, strawberry and tomato, are petals of this dot that represents red. And the green and the grape petal goes through the dot that represents green. And so we have this way of representing our function as a bouquet. Now I like this because it's a novel way of thinking about functions, and it lets us kind of see the bits and pieces involved and make connections with subjects like graph theory. It's also quite cute to think about what composition looks like in terms of these petals. So this blue function here is represented by this bouquet here. And then if we want to represent this red function, we could say, well, strawberry and tomato, so I'll just write S and T, they are mapped to red, and grape is mapped to green. And then if we just sort of pull in these black petals, we can basically represent what's going on with the composition. And so strawberry and tomato in the composition get mapped to 3, while grape gets mapped to 5. Okay, so now let's get on to way number 5 of visualizing a function. And so let's think about this function f here. So I've drawn it in the traditional kind of arrow. So I've drawn it with the traditional kind of arrow picture. We have this set x with elements a, b, c, this set y with elements 1, 2, 3. And here we can see how this function f works. Now, another way we can picture this function is as a graph. So in a sense, what we do here is to make things higher dimensional. So the key thing that we do is form this new set, which we call x times y. Now this is what we call the Cartesian product of x and y. And it's just the set of all pairs which have their first element in x and their second element in y. And you can see that that gives us these 9 elements here. A1, B1, C1, A2, B2, C2, A3, B3, C3. And now what we can do is we can represent our function f as a function from x to x times y. And all we do is if we have an element of x, let's say A, then it gets sent to the pair that has the first entry is A, and the second entry is where that A got mapped by f. So A here gets mapped to 1, and so A here is sent to A1, and B here gets sent to B1, and C here gets sent to c2, because if we look at our original function, f sends c to 2. So why do we do this? I mean, it looks like we're just sort of puffing up the dimensions and not really adding any extra information. But there's one very good reason to make these kind of graphs of functions, and that's to make connections with geometry. And so we know well that if we have a function from, say, numbers to numbers, like for example, a function which adds 1 to its input, then if we make a graph of it, like this for example, that can really help us to see what the function's doing in a snapshot. And I think it's very interesting to note that we can do just the same thing abstractly with sets, with this kind of idea of being able to take the Cartesian product of sets. And also this idea of graphs gives me a neat little segue into the next way of thinking about functions, and that is as a relation. So what is a relation, and how do we think of a function as a relation? Well, if we think of a function as a graph, and then we just take all the elements of x times y, which have something sent to them in the graph, then that subset of x times y is what we call a relation. And it's a relation which represents our function. Okay, so this green subset here is the sort of relation which represents our function f. So what is a relation in general? Well, a relation in general is just going to be a subset of the Cartesian product of two sets. So this would be a relation, this would be a relation, the whole thing, that's a relation. So a relation in general is just a subset of x times y. But if we want to encode a function as a relation, then what we want is that for all elements little x in the set big X, what we want is that there exists a unique element of y such that this pair x and y are going to be in our relation. Okay, so remember, a relation is just, and here when I say our relation, I mean the particular subset of x and y. So this gives us another way to think of a function. It's a bit more abstract. It's basically the idea that we can encode a function from x to y by pairing every element of x with a particular element of y. And so we're going to end up with a load of pairs, and we could represent that collection of pairs as a subset of the Cartesian product of x and y. So there's another neat way to visualize relations. So if we just pick some general relation, let's say this one here, this is a subset of x and y. It's not representing a function or anything, but there we go. Then we can sort of visualize what's going on in this relation by a structure which is called a bipartite graph. So we can see that here we've got the pairs A1, B1, A2 and B2. So we can represent them. A1, B1, A2 and B2. And you see all we're doing is that each pair is getting represented by a sort of connection, which is connecting one of the elements of x here with one of the elements of y. And so that's a general way of representing a relation. And then we can see that the kind of functional relations are ones that have these kind of bipartite graph representations, which really look like the kind of first view that we've had of a function, basically where we're drawing an arrow from every element in the first set to an element in the second set. So the next idea I want to talk about is a really powerful one that's very modern, and it's Spivak's notion of an ontology log. So the idea here is that we have these objects or nodes, And these are representing abstract concepts. Now, we label them with these indefinite noun phrases, but they're really representing sets. So when we say a mother, what we really mean is a element of the set of all mothers. Or for example, a parent would mean an element of the set of all parents. And then we have these arrows, which are representing aspects of these things, or sort of functional relationships. But the idea is that we label these functions or arrows in such a way that we can really read paths along these kind of diagrams or ontology logs as if they were plain English. So when we say a mother is a parent, we can think of that as a sentence in English. We can also think of it as specifying a sort of function, sending every mother to a parent. And when we compose functions, this kind of translation into language still makes sense if we add in words like which. So a mother is a parent, which is a person. That would correspond to this composition here. So another really neat thing we can do in these ontology logs is we can mark certain regions with a sort of loop to denote that if we compose the arrows or functions around the boundary of that loop, we end up getting the same result. So this notation in this case means when we do this function, a mother is a woman, which is a person, that's basically the same thing as doing this function, a mother is a parent, which is a person. Anyway, this notion of ontology logs is another extremely powerful one. Another way of thinking about functions and visualizing them and tying them in with everyday happenings. And if you want to find out more about ontology logs, you can check out my category theory video on everyday language. And so finally, we get to the seventh, and in my opinion, the best way to think about functions. And that is, of course, with category theory. So with category theory, we can think of sets as dots, which we call objects. So our sets just become dots. So this set of fruit from our first example is now just this dot. Colour is also represented by this dot. This set of numbers is also represented by this dot. And now our functions, we just draw them as arrows. So here's our first example again. We have this set of fruit, this set of colours, and this set of numbers. And we have this red function and this blue function here. And so now with category theory, this picture just becomes this picture here. And so it's pretty simple what's going on here. Instead of having these sets and seeing what's going on, now we just have these single dots, which we call objects. And instead of drawing how all the elements get mapped, we just have a red arrow for the red function and a blue arrow for the blue function. And so we're representing the sets abstractly as objects and the functions abstractly as arrows. But the key thing in category theory is that we do keep track of how we can compose some arrows to get other arrows. So if you remember from our first perspective on functions, I described how we could compose this red function and this blue function to get a purple function. And so in a similar way, we can say that composing this red arrow and this blue arrow yields this purple arrow. And so we're keeping track of composing, and so we're keeping track of how we can compose some functions to make other functions. So this is what category theory is all about. Number one, we like to look at things abstractly, and so often we'd rather represent things with objects and arrows rather than always having to open things up and look how our structures or our functions are working in terms of their elements. And number two, we're very interested in how composing some arrows can give us other arrows. So category theory is very close to the perfect language, in my opinion. And now you know about functions, you're in a good position to have a look at my category theory for beginners videos.